Now we see the second method, which is called the one-hot state assignment or encoding. This type of assignment is to assign codes to your states in your state transition diagram or your next state table. So in case of the one-hot assignment, we actually use one flip-flop for each state. So if you had like n states, then we will actually use n flip-flops. So let's say, for example, in this case, as you can see, we have 8 states that are here. In the case of our previous method, we are going to only assign binary values to it. So we basically will need to actually have say ceiling of log 8 to the base 2, which will be 3 flip-flops. And as you can see here, for the 3 flip-flops, you will have 3 state variables, either a C, B, and A. So, but in the case of the one-hot encoding, so we will have 8 flip-flops and we will have 8 variables. So for example, you will basically have it as A, B, C, D, E, F, G, and H. So you have 8 of these variables. And as you can see, the advantage of doing one-hot encoding is that it is very easy to actually get your equations for your flip-flop by simply inspecting the state graph. So we don't need to use K-maps. We can simply write an expression by just looking at the state diagram. So here is another example. As you can see, we have 4 states. In the case of the normal encoding, we would have used, or the binary encoding, we would have used 2 flip-flops, and we would have 2 variables either as A and B. But in the case of a one-hot encoding, so this is how one-hot encoding is performed at a given state, which is S0. So we have Q1, Q0, Q1, Q2, Q3 as your state variables. So we have this for one state, which is S0. S1 is represented like this, S2 and S3. As you can see, at a given time, only one of those state variables is a 1. So this basically follows a ring kind of counter. And so only 4 are used. So therefore, the rest 12 combinations are not used. So if you had, for in general, say n states, then by using one-hot encoding, you would actually need n flip-flops, and you would only be using n of these codes, where you have unique ones in every code, and 2 to the power n minus n of those other combinations will not be used. So here is a simple example. So as you can see, we are going to call our states S0, S1, S2, and S3. So remember, these are state symbols. We have one input, which is X, and we also have an output, which is Z. So this is our state transition graph. And so here we can see that from a state transition graph, we've got our next state table. And we are going to assign codes as shown here, where S0 is 1000, S1 0100, and S3 0001. And this order can be in any particular order. So now so once it's assigned, so this from here, you can see that we have assigned our codes to our state. And now how do we go about by writing the expressions? So simply, since we are going to use the D flip-flop, so we're going to actually simply have your next state expression, which is S0 plus, is nothing but D0 would be simply you look at the number of the arrows that are coming in. So we have one that is coming in, which is that, and the second one that is coming in that. So here you can see that we have x is equal to 1, and then similarly here x is equal to 1 comes in. So we can write this expression. We have x is equal to 1 coming in from S0, a self loop by itself, plus x is equal to 1, so x is as x coming in from S2. So therefore that's basically how you would actually write the expression. So if you had something like a state which is say x of say just to give you an example, x of say 5, and then you had 0 that is coming in from S2, 1 coming in from say S1, then you have 0 coming in from S3, and then you have 1 coming in from S4. So the expression that you would write here is since x is the value, you will write x dot S1 plus x dash dot x2, because it's actually x is equal to 0 there, plus x dash dot x3 plus, and you have x dot x4. So this will actually be the expression for this particular thing, which is going to be D5 or S5 plus. Okay, so similarly we can do that for all our combinations, as you can see here. So we are going to see it for S1 plus, which is this. We have 1, 2, and 3. We have 3 inputs that are coming in. So we have 1 coming from S0 with 0, 1 coming from S1 with 0, and then also we have another one coming from S3 with 0. So basically we have x dash S0 plus S1 plus S3. Similarly for S2, we have 2 coming in, one from S1 and another one from S3. Both of them are for x is equal to 1, so we have x S1 plus S3. So, and then for D3 we have only one coming in, which is from S2 with 0, so that's what it is. And now for Z, so you can see that we want to make sure where we have the 1, so it only is with respect to S3, so simply we will just write it as S3. Alright, so now we also need to convert that into our state variables. So even though we have these codes, which is S0, so our 1000 stands for our state variables. You can name it A, B, C, D. So here S0 is nothing but A, S1 is nothing but B, S2 by itself is C, S3 by itself is D. So just substitute that into the equations, and then you basically will get our final expressions. So here is the complete solution. So here you can see that now this is nothing but this was like S0, and then you can see this was a variable A, B, C, and D, and this is your D of A, which would be nothing but S0 plus, D of B, S1 plus, D of C, S2 plus, and D of D would be S3 plus, and that's the value of Z. So the value of Z is nothing but just D that is actually coming from, as you can see, you're getting it from here. So in other words, this all this are fed back to these state variables over here. All right, so next we see about the heuristic method, where we take into consideration the state transition, the inputs, and the output behavior.